Okay, in this video, I'm talking about system efficiency in terms of energy out that produces useful work versus the total energy in. All right, but before we get started, I wanted to briefly touch on the second law of thermodynamics that was in the Hagen reading assignment. We talked about it a little bit already, but I wanted to bring it up again because it's related to this topic. All right, so remember this experiment where we took a mass on a spool, we let go of the mass, and the mass falls and it turns the propeller, which in turn then heats up the water. See that red heat there? And if it were not a perfect insulator, this heat would leave the boundary of the system, if the boundary is the container, and you'd have heat coming on the output. Okay, so the second law of thermodynamics has to do with reversibility. That's part of it. And let's suppose we turn this around and we tried to put heat back into this system. Okay, so we add heat back into this system. Of course, we don't expect the propeller to start turning and then the mass starting to roll up on the shaft. All right, so these two processes are not reversible. Okay, so that becomes significant later on when he talks about a heat engine. Okay, so in the Hagen book, chapter 6, you skimmed over this, I'm sure, pretty quickly because it's not that easy to understand what they're talking about. But I wanted to talk about it a little bit because it has to do with efficiency. And if you're a mechanical engineer, you're going to take thermo and you're going to learn more about this. If you're an electrical engineer, this might be the only place you hear about this, and I think it's an important enough thing to know about as an engineer that we should at least talk about it in one place. Okay, so the idea here is to take a look at a heat engine, and what it occurred to me that you might not have a good mental model about what a heat engine would be. Okay, so a car engine is an example of a heat engine. A steam train engine is an example of a heat engine. Okay, so I put a YouTube video link. You should watch that about how a car engine works, just in case you've never seen something like that. But that'll give you an idea. Okay, so in this particular example, he's talking about you can take sources of heat, all right, and from those sources, you drive or supply energy to a heat engine. All right, so that's what we have shown here. Qn is heat coming in. All right, so like with a gasoline internal combustion engine, it would be, you have an air mixture with gas showing up in the cylinder. A spark plug ignites that. That obviously is a source of heat. Okay, so that's where the energy comes from. Okay. From there, we have work that comes out. Okay, so in the car engine video, the crankshaft turns. All right, we get useful work coming out. Okay, and there's still some energy left, some heat going back out into the low temperature source. All right, so if we take a look at this, we can think of this in terms of energy in equals energy out. All right. But some of the energy on the output is not useful to us. All right, so namely, I'll put a big red box around it. The output energy here, the output heat, may not be useful to us. Okay, and so when we're looking at the total efficiency of the system, what we really want to look at is how much useful work we get out. Okay. So what I know is that the first law of thermodynamics says that energy in is equal to energy out. Energy in this heat engine example, is Qn. Energy out is work out plus Q out. Okay, so if we solve for work, we get Qn minus Q out. All right, so that's just first law of thermodynamics. Okay, next, we start talking about efficiency. All right, so efficiency is where we look at the ratio of the useful work. Okay, sometimes people will call that the useful energy. Okay, same idea. So the useful work coming out of the system divided by the energy coming in. Well, what we know for the energy coming in, it was Qn. Okay, so I can rewrite this. Okay, so this gives me an efficiency, all right? And then he talks about in the Hagen book that if you have what he calls an ideal heat engine, okay, so the ideal heat engine is a concept, okay? It doesn't really exist in practice, okay? And the ideal heat engine is reversible. Remember, I just gave you an example of a system that's not reversible. And if you think about a car engine, you can't reverse some of the effects of the losses in a car engine. So a real system, a real heat engine, is not reversible. So we know that. All right, but if we had, this fictitious heat engine that is reversible, there's a result that shows that the ratio of Q out over Q in, okay, this is something you'd show in a thermodynamics class, is the same thing as the ratio of the temperatures. All right, so what that means is the very best we can do is an ideal heat engine, and so we get a maximum efficiency for this heat engine of, notice I can make this formula, 1 minus Q out over Q in. All right, so what we would have here is 1 minus T out over T in. Okay, sometimes this ideal heat engine is called a Carnot engine, okay, and it's a well-known thing in thermodynamics, okay. So this gives you the very best you can do in terms of efficiency if you're given a temperature difference between what the start of what's going in as energy to the ideal engine and what's coming out as energy, okay, or as temperature. Okay, so that gives you an idea, and we're starting to talk a little bit about efficiency. All right, so let's move back a little bit, or I guess you'd say forward instead of backwards. We're going to talk about efficiency more in terms of energy into a system and useful energy out. Okay, we're not looking at theoretical maximums here like we did with the Carnot cycle or the Carnot engine. We are looking at, here's some energy coming in, here's useful work coming out, and what we have happen is there's some type of energy wasted in the system. Okay, so a car engine will have that, right? You put in gasoline, it burns, there's an energy source, but we know that there's friction forces within the engine, there's friction forces that have to be overcome, and the engine is not perfectly efficient. All right? Usually in the form of heat is what you see as the waste. Okay, so if we look at that, then the efficiency is going to be the output energy over the input energy. So you notice this is not really a violation of the first law of thermodynamics where we talked about En is equal to E out, because we are redefining what E out is. It would be useful work. It might be even better to be real precise about it and call it work out instead of energy out. All right? So that's the idea. All right, so the next thing I wanted to talk about is if you had some energy conversion process. All right, so energy conversion. It's not uncommon to have these cascaded. All right, so in this example, let's start with energy coming in, E1, and let's make this first system a gas turbine. Okay, so we're burning gas, some kind of gas, creating heat. It's turning a crank. All right, so we get some shaft rotation. And that operates at a certain efficiency, A/1. Okay. From there, this might turn an electric generator. Okay, so you have some coils, some windings. It goes through an electric field. The shaft is making this thing turn, and it generates on the output side electricity. Okay, and we know current moving through a wire is kinetic energy, and voltage is potential energy, and so we have this combination of energy in an electrical system. Okay, so from there, we might use that electrical energy to turn on a light. Okay, and so out comes some energy in the form of light. All right, so there's a conversion process. There might be a certain efficiency with the generator, and then there's a certain efficiency in how much energy gets into this process of creating light. Okay? So if we looked at E1 as the input and E2 is the output of the first system, then on the second system, E2 is the input and E3 is the output. And on the last system, E3 is the input and E4 is the output. Of course, in terms of reversibility, not all these systems are reversible. You can't just shine light and have electricity be generated without some type of, there are photodetectors that can do somewhat that, but you're not going to get it on the scale that you put energy in. A generator is a little bit more reversible. Okay, you can run it as a motor, turn it backwards, run it as a generator, but there's some loss going back through the other way as well. Okay. All right, so there's the setup there. So let's color these blocks in, just make this look a little more clear. All right, so if I was going to look at the output, the total output is E4 and the input is E1. All right, so you could get that as a combination of steps. Okay, so first of all, you get E2 over E1. All right, and then you get E3 with E2 as the input. I'm writing down efficiencies here. And then you'd have E at the 2. All right. Then you'd have E4 over E3. So notice each of these are efficiencies. A/1, A/2, A/3. And mathematically what we see happening is these cancel and I get the original relationship. Output energy, the useful part, the part that's light in this case, over input energy, okay, the gas that we put in and burn to generate energy through the gas turbine. Okay, so it wouldn't be uncommon to have efficiency sort of in these ranges for these processes. So maybe a gas turbine runs at 0.35. Okay, and then a generator is a little better. Let's say maybe around the range of 0.8. Okay, and then converting electricity, energy from an electric source to light is not very efficient. And let's say that's around 0.1. Somewhat guessing at these numbers. Okay, so you look at the overall efficiency of this system, E4 over E1, it's just going to be a product of these things, and you get a pretty small number for the total, 2.8%. All right, so that's what happens when you string cascaded systems together. You have losses at every stage. Okay, but it's something to think about. It's something to know about. We're going to use these ideas when we do a little project this week, where we're going to look at converting electrical energy into rotational energy, and we're going to use gears to kind of change the speed and torque characteristics of that energy. All right, and from there we can do some work of lifting a weight. All right, so we'll be using these ideas and talking about the efficiency of our system.